Hello, I'm Ludovic, and in this first video I will show you how you can use SaLinA to implement agent, to compose agent, and to execute agent over a workspace. So I'm taking a very simple example here. So what I want to implement is this set of equations. So as you can see, it corresponds to a sequential decision problems where you have one variable at which is defined as random for the first time step and which is defined with respect to b of t minus 1 for the other time step. You have another variable which is bt, which is defined with respect to at, and then you have another variable which is ct, which is defined with respect to at and bt. Okay, so let me show you how we can implement this different equation in SaLinA. So here I wrote the three equations. So what I need to do, of course, is to import SaLinA and to import from SaLinA the definition of an agent and of a workspace. Okay, and then I will implement different agents. So I will implement one agent computing a of t, I will implement one agent computing b of t, and I will implement two different agents to show you two different ways to implement c of t. So let me start with this a agent. So a is an agent. Remember that in SaLinA an agent is also a PyTorch module. So you can initialize your agent like classical PyTorch module. And then to implement the agent, you have to override the forward function. And this forward function, you can define multiple arguments. So here, this agent will act at time t. So we'll use a t argument to define the time step. And then if t equal to 0, the value of this agent, this agent will compute a value which is a random vector. So in SaLinA, all the agents are acting over batch of values. So we need to define a batch size. So here I will choose a batch size like this. So it will generate 32 random values corresponding to 32 set of equations actually. And if t is not equal to 0, then the value is b of t minus 1 times 1.2. So first I will get the value of b at t minus 1, and then I will compute b times 1.2. This value function, then I will write it into the workspace under the name a. So self.set a of t equal value, and then I can do the same here. Okay, so what you can see on this agent is that my agent is not returning a value. My agent is reading values from the workspace and writing values to a workspace. And this is the way we define agents in SaLinA. Okay, so now I will implement the second agent, which is this b agent. I will do the same. So b is an agent. I can initialize this agent like this. And then in the forward function, this is an agent acting at time t. So I need a t argument, but this agent is also using a epsilon value. So what I can do is add epsilon as an argument of this agent. And then this agent will first read the value of variable a at time t, and then it will compute B and write B into the workspace at time t. Okay, so now I have these two agents, A and B, and I will show you how I can execute this agent to compute this A of t and B of t value. Then I will show you how we can implement this C agent after. So I define my agent A of class A. I define my agent B of class B. And now one simple stuff I can do is to create a new workspace, and I can execute this agent through a simple loop. So for t in range of, let's say, 100 time steps, what I can do is execute A over the workspace, and then I can execute B over the workspace, at time t, and here at time t with epsilon equal to, let's say, minus 0.3. Okay. After this execution, these agents have written information into the workspace. So what I can do is that I can print the information that is in the workspace. So I can access this A and B variable in the workspace like this and just print their value. Okay, let me test this code. So in order to test this code, I just have to execute my Python file. Maybe I have some errors. Yes, I forgot to import Torch. Okay. And I have another error. What is it? Line. Oh, it's self here. Sorry, like this. Okay. And here what you can see is the value of A and the value of B. So if we print also the size of these two variables, so let me print the size of A and size of B. So what you can see is that the size is 100 time steps times 32 batch size. Okay, so it's quite simple, but then maybe I don't want to write this loop every time, so I would like to have a single agent able to do this computation. So what I can do is replace this, and I can compose the agents together. So first I will define an agent AB, which is a combination of agent A and agent B. For that, I'm using this agents class that I have to import. Okay, and the agents class is just a way to get a new agent that will first execute this one and then execute this one. So now that I have this agent, I can simplify my loop and just execute agent AB at time t with an epsilon value of minus 0.3. Okay, so it's a way to avoid to write these two lines. I can combine my agents in one single agent and then execute this single agent. Let me check if it works. Sorry, so this agent is in the agents directory. Okay, and then I obtain exactly the same output than previously. So I still have this A variable of size 132, B variable of size 132, and the rest. Okay? But I still have this loop over the time steps. So SaLinA also includes a way to simplify this implementation. And for that, I will define a new agent that I call temporal agent over agent AB. This temporal agent is one of the agents provided by SaLinA. And the goal of this agent is to execute one agent over multiple time steps. So now, what I can do is just execute this temporal agent from time 0 and for 100 steps with the value epsilon equal to minus 0.3. Okay? So at the end, what I did is I defined two agents, then I combine this agent into a single agent, and I execute this single agent over a workspace. It still works, and it still computes exactly the same output. Now, let me show you how we can implement this last equation, which is about CT equals to AT plus BT. One way I can do it is by defining a new C agent. So let me do a copy paste. Okay. So this agent will read the value of A from the workspace at time t. It will read the value of B. This agent will be executed at time t, and then it will compute C equal to A plus B, and then you will write this value into the workspace. Okay. So I have a new agent, and what is nice with SaLinA is that I can just build this agent. I can just add this agent in my combination of agents, and then I can keep exactly the same code, and my software will compute this new information based on agent C. So it's very flexible, and I can write the value of this C variable here. So I do the same. I just write the size and the value of C. And now, if I execute my code, then I also have this. So I have this A variable, B variable, and C variable. Okay. So what you can see here is that because SaLinA allows you to combine agents, it is very easy to add, remove, replace different agents in the computation without modifying the rest of the code. Okay. Here, my agents are all working at time t. Okay. It means that when I am executing this agent, I am executing at time 0, 1, 2, 3, 4 through a loop. So it can be slow. But this C agent, typically, it can be computed after the computation of AT and BT, of all the AT and BT. So I can define another agent to do this computation differently. So C2. Let me copy paste again. But here this agent will not act at time t. What you will do is get the complete value of A, so the value of A for all time step, the value of B for all time step, and then it will write the value of C for all time step. So this is not an agent that I will execute at each time step. I will first execute A and B at each time step, and then after that I will execute this C2 agent over the workspace. So the code will be a little bit different here. I will keep this agent AB. I will execute this agent AB to compute A and B. Let me print after these computations the variables that are in the workspace. So here, if I execute my code, what I see is that the workspace contains two variables A and B. And then on top of this workspace, what I can do is execute agent C2 over the workspace. And instead of making use of a loop to compute all the CT values, then it will be computing just one sum over the complete tensors. I can execute it, and then I see that after this second execution, I now have in my workspace this C variable. Okay, so this is another way to execute, to do this computation. What I mean is that an agent can act at time t, but you can also define agents that are doing global computations over the workspace. Now, if I really want to have just one agent at the end, I can also combine this agent C2 with the other agents. So one way to do it is to use this agents class. This agent will first execute T agent AB, so the temporal agent. Then this agent will execute agent C2. And I can execute this agent over the workspace like this. And if I launch my code, then you can see that this agent has computed the three variables A, B, and C. Okay. So at the end, whatever the way I am doing this computation, I obtain one single agent that I can execute over a workspace to compute the different values, the different tensors I need in my model. And this is it for the first video. Thanks.